Mike, welcome back to another stream of Advanced R. I've been MIA for a couple days now. I was trying to get on a schedule where I'd go on every other day and just being transparent about it, with having been out of town for the weekend. I sort of messed up my streaming schedule, admittedly so, and now I'm trying to get back onto it before things get busy. I am still a grad student currently, so a lot of my time gets dedicated to doing graduate school courseworks since I'm still early on in my time in graduate school, and my research projects. So normally I have a pretty good schedule about those sort of things, and that facilitates me doing these side projects that are intellectually stimulating, to say the least. Not to say that I don't want to give the sense that PhD is not those things. It's just a way to more comprehensively explore material I might not be diving deeply into in my graduate studies. So in the cognitive sciences or in decision neuroscience, I get to study a lot of cool things, and I don't get too often to dive deep into programming unless it is programming for a particular task. And it is still an area of work that I'm curious about, and these streams give me access to exploring them. And I hope to use this channel and platform to explore other things that I'm interested about in the future. So, like, I've been looking into doing these robotics challenges. Well, I'll have like a camera above me, and I'll be able to show like step by step what I'm doing, about how I learned about robotics from scratch. So I personally don't know much of anything about doing these small electronics projects or working with robotics or the types of programming that involved in that. But I think it would be useful to document the progress as I learned a lot about those things. Additionally, I want to do like a drawing challenge where I learn how to draw and I show my progress on stream and talk through some of the particulars about aesthetic decisions that I make. And on the topic of aesthetics, I also want to do this graphical data visualization project. So there's a lot to come, and I think that this channel could be a container for much of those topics. But that's the future, and we're not going to talk about any of that, as exciting as it is. Today we're going to talk about and continue our discussion on Chapter 3 in Advanced R on vectors. And I do want to note that I have been moving ahead in terms of my reading of the content, but I want to make sure that I get to at least go over all of the foundational content. And by foundational, I mean all of the content labeled as the foundations in the book. Foundations, so these 8 chapters. I want to be able to go over at least those for the stream, and then we'll explore the other topics as we get to them. But this is important because I'm also trying to translate and document this onto YouTube, and I think the 8-chapter content might be what a lot of people get to and then they pick around. So it's important for me to cover that stuff. Plus, gotta practice foundations. So last time on vectors, we had just finished S3 every time. we just finished S3 atomic structures, which is a structure which is really just adding particular metadata or attributes to an atomic vector such that it gives it different types of characteristics that you can then, when fed into functions, makes it so that the object will behave differently. And the object just behaves differently in R. Okay, but we're going to move into the second of the two most important vectors, lists here. And just a reminder, atomic vectors are such because all the elements contained within the vector are the same. Lists are a little trickier and different because they're going to be able to contain elements that are different from one another. So each element could be something else. It doesn't all have to be a double or a numeric, for example. You could have a character vector, and you could have, as shown right here on the screen. Sorry, sometimes I forget that you guys can see the screen too, but this is why I do it up here in the first place instead of downstairs. I might get better signal or frame rates downstairs, but I don't get my setup. So I don't get the second monitor and I don't get my microphone. And until I sort of negotiate moving this stuff downstairs in a place where I could have a pretty nice setup, this is what we're working with. So we're looking at the screen. List. So you see here just this structure list. It contains vectors that are reference to different data types. So in the first one we have an integer, character, logical, and numeric, right? And lists can contain all that. And in fact, lists are interesting because they can also contain lists. So the structures can get very hierarchical and complex in terms of what they can contain, and you'll see that we're going to take advantage of a lot of the flexibility that lists provide us. Cool. So here we can use object size to look at some of the efficiency in lists. So you'll notice here that lists, when they reference, for example, an object like the empty cars, which is a standard data set, that we don't get that much increase in object size, and part of this is just empty list elements. So recall that objects reference, or our names are bound to or referencing values, and this is a case where they're all referencing the same data set, so R is going to be able to efficiently access this. So this can contain more complex structures. So this example here is just showing this up here is in diagram form. So these four, where each of the lists are wrapped around these boxes, and they have the contents of the list organized like that. So this can be recursive, as I was describing before. So we have list and list and list and list, which is kind of fun to say, but it ends up looking like this, where each of the boxes represents a deeper structure in the list. And this is actually something that I'm really grateful that I'm getting exposure to right now, because for one of my projects, and just move it back out into application again, one of my current projects involves coding up a experiment in HTML and JavaScript. And currently how I have it set up is the output, or the data that I get from someone participating in the experiment is in what's called a JSON structure. We won't get into the specifics of that, but JSON and how it's structured, when you move that structure into R, you get a bunch of lists. And in fact, you get these hierarchical structures of lists based on how I set up my experiment. So I actually end up with lists within lists within lists within lists that reference what I'm looking for. And having been exposed to this chapter has really given me a much more solid groundwork to start approaching how I'm gonna tackle extracting information from these complex data structures and reformatting it into, well, this is for a different topic, but reformatting it into what's called tidy data. That's for a book that I actually don't have a copy of anymore, but it's for R for data science, and maybe we'll go through that book sometime too, because I could for one use the refresher, or it would be at least fun to go through that material with people, and that might be more of interest than some of this more esoteric information about the R programming language. But nonetheless, we can keep moving here, and we'll look at how this structure sets up a list. But in this case, we have a list, and then in the list, we'll have a vector in the list. So then you'll notice that this gets double the amount of structure, while this is just retained within the list. So you can combine them and their uses, or you could combine these two and then make a list around this one. This is interesting. So you can see the differences in what happens here. So just comparing the results, we see here we have this big list that contains it, and this is in that first list. This is another list as shown here. But for this one, everything gets just coerced into a single list, it looks like. So this list kind of cancels itself out, and then all 1, 2, 3, 4, from what it looks like to me, just get put in a list. Yeah. Oh, and you can look at the outputs here, sorry. So this just ends up being a list, and then this. So something about this coerced or changed the output for the data structure. So I guess that's what we'll talk about next. So, or maybe this will get at why this might be the case in the next section. So here you can look at type of and Islist are going to be the ways that you assess or coerce data types to list structures. So if I wanted to know if something was a list in the first place, this is the way to do it. And this maps onto techniques that we have talked about before, where we wanted to coerce information into various atomic vectors, like numerics, for example, or doubles. Or if you wanted to ask if they are those structures. In addition, you can also unlist things. And unlisting's tricky, and I, once again, just reflecting back on that project that I've been working on about wrangling some of the JSON data. Unlist gives me a very bad answer a lot of the times, I find, and I've gotten the best results when I do some sort of subsetting the data, and then unlist is like the final thing I do to get me a clean vector, or at that point maybe I don't even have to do an unlist procedure, but that might not be the best workflow for right now, but that's the workflow I'm going with, right? Anyways, that's how we assess lists. So we can look at then the equivalence of matrices and arrays to vectors that are lists instead of vectors that are atomic vectors. So this was kind of interesting to me this was pretty interesting to me at first, because I didn't think about it, but you can create list structures that have matrices dimensions. And a lot of this is for just organizing information in a way that's more palatable to human cognition. You can't do, at least from my understanding, you're not going to do a particular type of computation on a list structure that would be best suited for, or will be best implemented by a matrix or an array. What am I trying to say here? If I was going to do a computation on a matrix and an array, I would do it on that in an atomic vector form, not in a list form. And so doing this in a list form seems like it less computationally taxing. And the example it gives is actually a good one when you're working. The example it talks about here is, say you were working with some spatial temporal data of some sort, and you knew that there was some organization of the data that could make either accessing it via some loops, or just when you're conceptualizing or representing the data in your mind, and it had like these observations are over here, these observations come out in this sort of order over time, and that's the type of thing that I think can be gained from using a list in that has multiple dimensions. Or at least that's my first thoughts on it. Man, it's cool to think about. Like I could have a 4x4 grid here, and each of the 4x4 grids could contain lists, right? So this is just organizing my list so that each of the lists that I have in my list can be accessed in a way that's like clearer to the representation of whatever the data was. Say I had 4 treatment conditions and they were related, or I had a 2x2 factor design of sorts. So this is 2 factors or 2 factors, like male, female, pre and post. So I could have like pre-post. I guess I could do this here. Yeah, we'll do that. That's a good example. So for example, this is, I guess, this is what comes to mind when I think about what could be a good example. So here I have lists, and then you could have like pre, post, and we could have male, female, right? So now each of these have a list, and if I went and looked in here, I could look, oh well, I got it wrong. It would be pre-male, post-female, something like this. Okay. So now if I look at my list, right, so now I have pre-post, and I have male-female, something like that, and then each of the elements within it could be the contents of, I don't know if I can just name these structures here. That would be cool though, if this was like, I guess I could check if I could just name that free. Cool. Maybe. And then if I looked at this. Attributes of the list. Class. Feature yeah, I can't really get that information in list names. No. Okay. Yeah, so this naming of the list doesn't seem to be doing anything to the structure, but you get the idea of just using the structure to your advantage somehow. And I'm noticing here that when I'm doing computation in R, that's when I get the largest amount of depreciation in frame rate. So my computer struggle busing, and I really do try to shut a lot of stuff off, but whatever. Okay, list all the ways that lists differ from vectors. Well, first off is that they can contain different elements, and I think that's one of the crucial factors. They have this hierarchical structure to them. I don't know if in principle or in technically that a set of a vector contains, or its elements are vectors in themselves of size 1, but that only goes so far, right? Because if a vector contains vectors, it still can only go like second order. In that case, like we have vectors that are vectors themselves, But lists can go deep in the sense that you can have lists that have lists within lists, and these lists have lists. Those lists also have lists that reference lists. You see what I'm saying? So why do you need to use unlist to convert a list to an atomic vector? Recall that as vector here references the structure or class structure and not transforming something to a vector per se. It's more about the particular attributes associated with the vector object of interest rather than making some assessment about if this vector is an atomic vector. Now, that's why we would need unlist. So that answers that question. So compare and contrast the combine and unlist when combining a date and date time. As we know, I'm not going to do any of the questions about date and date time. Sorry for those interested in that. I encourage you to go and try it yourself. But I won't be covering any of the material about date time manipulation. I would recommend checking out the documentation on the lubricate, I believe it's called lubricate package. Hadley Wickham, of course, is involved, and the team, the dev team, have done what I assume to be a fantastic job at making that an accessible package. But we'll just move to talking about DataFrames and Tibbles now, which is arguably one of the most important S3 vector structures. And if you use R, you're probably really familiar with DataFrames and Tibbles, though you might not know what makes them characteristically different. You'll just notice that sometimes when you do analysis, things get putted in their Tibble or their DataFrame. Well, here we'll go into some of these particular differences between the two structures and why you might get sold on using Tibbles, but even today, I was just having a hard time using Tibbles. Tibbles are being stubborn with me, so maybe that's partly a good thing, and I should think more critically about when I put things into these S3 objects, but nonetheless. So just like when we think about, let's set the bigger picture, but just like when we think about atomic vectors and how when you add dimensions, you add this metadata, these characteristics, attributes, you get functionally different data types. Here, lists are built then or can accommodate the data frame and the Tibble. So it's adding information via the attributes that make it so that the data structure type, a list, can do numerous things that are very useful, particularly in data analysis and data analysis. Maybe data storage and storing well-wrangled data, also something that you do for this kind of structure, right? Okay, so let's move right into it then. Now here, data frames, you can create a data frame just like using this command here, and you're going to be able to give the columns names, and then you're going to give the reference of the column to some set of values. Here is 1 to 3, and then just like in the case of a list, each of the columns can contain different sorts of types of elements. So if we looked at the attributes of this particular data frame we just created, then we have these names, and we have class, and then we have row names. Now recall that names is one of those names is one of those attributes that tends to be attached to data structures. And in this case, the class data frame is what makes this particular object, an S3 object, a data frame. Okay, and then we have these row names, and row names are going to get tricky as we move forward. We'll see. Okay, so in contrast to the regular list, we have some constraints here. The length of each vector must be the same. That's right, because we're trying to create a structure that facilitates organization in our data. So adding a constraint that it must be what's called rectangular is more of a feature than something to be thought of as like a hassle. If you wanted structures with different numbers of rows, then you could just use a list or hold the structures independently, but data frames we want to organize in some way, right? So a data frame then has rows, names, column names, and just has names. So you can also look at the number of rows and number of columns, and the length will give you the number of columns, right? Not the number of rows. Which isn't intuitive at first, and I know for me, when I'm doing for loops, for example, I always write length, and I really, in those cases, don't mean length. So something to second guess when you're using or looping across data frames. And we'll talk more about this in chapter 5 when we talk about flow, which I think is such a cool concept and cool name. Big idea in R, right? It's just talking about the importance of data frames here, and then setting the stage for some motivation for the Tibble. And you'll see that the Tibble is what they call lazy and surely. Do less, complain more. So that's the annoying part. They're going to do less coercion, and it's also going to complain to you via the console when you're doing things. And these complaints are well-mannered in the sense that they're here to, that's kind of nicer, they're here to help guide you as you structure your data, not to harm you, but they might end up being harmful and annoying, as we'll see. That's kind of nice. I like putting the mic here. Okay. So Tibbles structure as data frames, and in fact, if you looked at the class structure, Tibbles are just more stuff, and data frame, the difference is longer because that's this. And we're going to talk about some of the key differences in behavior between the two, and I'm just really going to try to dive in and focus on these particulars because I think that's the biggest section before we get to the end of this chapter to talk about. Okay, create data frames using this form, and you can look at the structures here. You can get the names of each of the column, or you get the characteristics of each of the columns by looking at structure. So by convention here, this is a default. So this is kind of going to be the contrast we're going to talk about. We're going to introduce a characteristic of the data frame, and then we're going to talk about some of the issues or challenges with that, and what the Tibble attempts to do to address that as being this new and improved version of what the data frame is, arguably, or at least by some of its designers, they would say. So here, string factors is equal to false is something you have to be explicit about, because strings as factors will happen, I believe, automatically if we're not explicit about that. Beware of the default convention strings to factors. To suppress this, keep character vectors as character vectors. And as we spoke about before, you shouldn't be coercing character vectors to factors unless needed, because you are doing a substantial change to your data structure. Recall that a factor is an S3 object that is related to an integer. So you're changing your characters to integers, and this sort of change, especially if you want to do some string manipulation down the road, isn't what you're looking for. So you don't want behavior like that. And it's strange that this is the default behavior. However, Tibbles, you can do similarly, but it won't coerce your inputs, i.e. it's lazy. Tibbles not going to change anything about what you give it. What you give it is what it gets. It's a good way to think about it. What you give it is what it gets. But yeah, I mean, it's a feature. DataFrames automatically transform non-syntactic names. So we talked about non-syntactic names in the first chapter, or at least the names and values we talked about it. Yeah, names and values in chapter 2. So if you want to see that content, I do post all of this material on my YouTube channel as well, so you could go back and take a look at those earlier videos, or just, you know, go explore the content yourself. But if you're interested in also learning along with me on that content, then that's where you'd see it. So it's going to change the names, and it's going to use this change names procedure that we talked about previously. But Tibbles, they won't do that. So they do, however, because it's a non-syntactic name, they do add these dashes. I don't know what they're called. So it's not going to change your name. It's not going to force a change of name, but it is going to make sure that the name abides by the rules of names for things in R. So we still have this same DataFrames and Tibbles alike both need to have this constraint where they're the same length across the columns. However, when you give a DataFrame and a Tibble a reference to a name value pair, and it's a different length, they're going to behave differently. So for example here, in this case, we're assigning x124 and y112, referencing them, or whatever you want to call the procedure here. But you'll notice that 1 to 4 is longer than 1 to 2, and by definition here, this sort of structure isn't going to be compatible with this. So it needs to do something to accommodate this. It could throw an error, but instead R tries to resolve this by just doubling the contents of the value of y, what it calls recycles. So such that it reaches the length of the longest column. So here, if we have 1 and 2, it's going to fill 1, 2, 1, 2, 1, 2. But here, if it's 1, 2, 3, notice it can't repeat the structure. So it can't give 1, 2, 1. 3, it's just not compatible. It's not going to be able to recycle the contents of the name value pair. So it's going to throw an error. In the case of a Tibble, though, Tibbles are going to throw an error if the value in the name value pair is not 1 element length. And you can see that here, where if it was 1, it's smartly, I might add, because there's a lot of cases where you just want to create an arbitrary column that you're going to insert values in later down the line, but you want to just retain the structure. And so this helps you do that, but it's not going to let you do it in such a way that the values of the size are going to recycle beyond the length of 1. So just like here, this is this is a case where you could think about how DataFrames and Tibbles are going to behave differently with the same set of arguments. Okay, now we'll go over another difference here, and it happens during construction of the Tibble. Oh, this is kind of cool. And this is something that I didn't think about, but now I realize. Tibbles are going to let you use structures that are created before other structures in the data in the Tibble. So what this is demonstrating here is that we created X and labeled it 1 to 3, and now we can also create more additional name value pairs using later assigned name values, or using previously assigned name value pairs. So in this case, I'm assigning x in here, and then in the same set of arguments, I can assign y. And this is because what happens under the hood, inputs evaluated left to right. So now we know x exists in the Tibble. So I'm going to go ahead and just use x, and I can create this. And that's going to be, well, to be frank, I haven't found that to be particularly useful, but part of that might be a function that I just hadn't had the knowledge that this was, you were able to do this sort of thing. It's never been highlighted to me before. So if I had to just sort of pontificate on what might be the use of this, variable transformation for one, like if I wanted to standardize a variable I was putting in my data frame, then this is something I would use. So the example is like, say if I was getting response time data, so this response time data involves, say I presented a picture on the screen and I wanted people to press a key as fast as they could recognize the picture, I would get out the amount of time that it would take for them to press the key after having been presented the stimulus. This is known as a response time. And now something about response times that is sometimes conventionally done, not in all cases, but what you'll find is that the distribution of response times tends to be skewed, and you can, when you're doing linear modeling specifically, you might be of benefit to you to take some sort of transformation of the response times. A common transformation used is a logarithmic transformation. And so the example here that comes to mind is just if I was creating a Tibble and I wanted to get my response times, my RTs, I could also just make another, in the same function, I can make a logarithmic transformation of my RTs, and I'd have those available to me. That's sort of a long-winded explanation to describe it. So that's one of the most useful examples I can think of. Another example that comes to mind that I'm not sure if this would work. This might be a little too convoluted, but maybe we'll give it a go. Okay. To say that I have x and I want just some 100 observations of x, and then say I have, I don't know, I want these observations to be strictly positive, so I'm just going to add 10 to it. Okay, so now they're all positive. And now say I want to create this, oh, and now say I want to create y, and y is a function of x plus some random noise. So we're going to do this 100. Right, so now x and y are created. So now in this case, or maybe this is what I was thinking of. So say on data analysis, and I wanted to define x in this way, and then I wanted to define y in this way, and then lastly, and this might not work, I wanted to define model and such that I could do like a linear model here of y is a function of x. Oh, I didn't load Tibbles. It would help if I loaded the structures. So we're gonna need the tidyverse. Load the tidyverse, and now let's play around with this. Let's see. All columns in a tibble must be a vector. Is an LM object. But maybe I can just slap a list around it. And then we'd be coolio, right? Haha, this worked. Cool, so what I get is I'm going to get the value of r, the value of y, and then I'm going to get this object here, and it's going to contain my linear regression. This is kind of funky now because I believe, if I'm not mistaken, all these linear regressions are the same. Yeah. So they're not different, but this is a case where you might be able to do something cool with this. Maybe 100's a little egregious. Let's do 10 so I can actually look at the structure. There we go. So here, because a model list is size 1, Tibble is going to recycle the object across each of the rows so that it matches the length of our longest column, which is 10 here in this case. And you can see just by looking at the small sneak peek of the model object that each of these linear regressions are actually the same. And so this procedure might not be of use, but you can see a more general principle coming out of this, where if I had some set of observations from a given individual, I could also then have a column that contained the model output for that particular individual. And then we would have duplicates of that object for that subject, which I don't know how efficient that is in terms of memory storage, but it could be convenient to have all of these model structures set up like this. I don't know if I would use a list per se. You could also use a Tibble, I think. Oh. Nope. You can use a DataFrame though, I think. Nope. You can only use a list. And in fact, maybe I want, it might be easier to do something like this. So Broom is this package that gives you nice outputs for structures like a linear regression structure. So in this case now, instead of getting those annoying lists, I'll get a data frame inside of my Tibble that will contain all of the particulars from my analysis. And this is really nice. So in this case now you could imagine having a set of subjects and then having access to the model objects for those subjects within the Tibble structure. And that's pretty cool and something I don't take advantage of enough, but I have been using more recently for some simulation work that I've been doing for what's called a power analysis, which is just an assessment of how likely I am to identify a particular effect of interest, given that it actually exists in the first place. And this is not a statistics lecture, so I'm not going to talk in depth about power analyses per se, but commonly for more complex analyses, you're going to be using simulations instead of being able to analytically solve for the answers for the power computation. And so with that and the use of simulations, column lists are a very useful tool. And recall that because the Tibble is a list, this is a column, that's a list, and it contains lists that are data frames, right? And then in here we have this information. So very cool stuff, very useful. I won't dive any more into that. Let's just try to crank through the remaining content of this chapter. And then next time we'll start up with subsets and subsetting. And that will be cool because subsetting is generally a phenomena of interest or capacity that I'm interested in both theoretically and for practical reasons. Yeah. But we won't talk about that right now. So, okay. Data frames normally are supposed to be shown like this, so showing its attributes for the details, but that takes up a lot of space and is not as intuitive as writing it out like this. So if we wrote it out like this, then it's going to show all of the attributes or the metadata surrounding each of these lists in our data frame, or Tibble, but we're going to write it like this for convenience, and it's going to give us that structure that is really familiar when we're looking at those objects in the first place. Okay, so now we'll talk about row names quickly. Recall that when we were looking at these structures here, you notice that we just have 1 to 10. And in fact, if I were to just take data analysis here and look at the attributes of data analysis, you'd see that the names of the rows are just 1 to 10, like what we saw. And so row names is this tricky, what I think Hadley would call archaic part of the data structure, and can create weird sort of setups here. But you can set them, so instead of having numbers, right, we could make Bob, Suzanne, Sam here. And it gives us that matrix-like look and feel. When you think about TwoDay structures, you think of that, right? But they're not interchangeable. So here's the trick. So you can't a transpose of a data frame isn't going to give you the data frame. So it's not desirable to have row names, and this is just making an argument for the abandonment of row names, which sets up the motivation for why Tibbles don't or won't use row names. It's just a poor abstraction. They have to be unique, which is weird. So, for example, if I had a bunch of structure, this would be cool if it could work like this, but Bob, I couldn't have a structure that said Bob, Bob, Bob. So it's not like I could use row names to organize my data for clusters like subjects. So if Bob was one of my subjects, I couldn't just have a bunch of Bobs. I have to have this, Bob 1, Bob 2, 2. So that's annoying. So for this, Tibbles, they don't have row names. So Tibbles don't have row names, different recycling procedure, less coercion in terms of the changing of structures. Yeah, that's it. I mean, that's not it. Those are all very important sort of things that we can do. Okay. But you can, when you make something into a Tibble, it can or will make row names into a column. Here. So row names could be equal names. So if you had a data frame with names like this, you can just name the column something and it will change those into the values. So this might be common in the case where you organize data in a, oh, this is a good example. So say, oh, this is actually tough here because trials let trials be equal to row names to column. I'm not sure if this one. Yeah, it's not gonna look like that, but I could do something like this. So I could just use a pipe operator, which I'm sorry, I know we haven't talked about that. And then you can make the name trials. And this then is going to give us the row names extracted and then given their own column, which is cool. It might be of use for cases like that where I had some ranking or temporal information embedded in the organization of my data structure, in this case the Tibble, and I wanted to pull that out so I didn't lose it when I coerced or changed my object to a Tibble object. And so this is a nice case where instead of having to write out like 1, 2, 3, 4, 5, 6, 7, 8, 9, you can just port over that information and use it for whatever your purposes are. But to do so, it looks like at first glance you're going to have to use the pipe operator, which is just, you can think of it as, and we haven't talked about this, but, and then. And I know that this stream is a more intermediate level stream, so I don't have to explain what the pipe is, but yeah. This code is going to give me a column named trials containing the row names. So it gives me row names. Okay, printing. Most obvious difference between Tibbles and DataFrames. Oh, here's another difference, printing. Okay, I almost forgot printing. Okay. We won't talk about printing in too much depth, but you'll see here that a data frame and a Tibble are going to print differently. So Tibbles are going to print characteristically or only the first 10 rows that fit on the screen, and columns will all show on the bottom here, right? So we're not going to get, or we're going to get a particular summary of the information with the default print statement. And color is also used in the console. In this case, we don't have any. Oh well. I guess maybe we could get some color though if we say made Z an object. Z is just x minus 10. To now, maybe, I just want to show a little color. Here, got it. So now, when we printed data analysis, you can see how negative values are going to get this red. That's kind of cool, and something that you might use in package development when creating user-friendly outputs. You might want to take advantage of this coloring. And I know that I haven't found the coloring particularly useful yet, but it might help point out some. And part of that might be a function of I do a lot of my analyses in R Markdown, and as you saw previously right there, R Markdown isn't going to give you the color here when I print something out from a shoot, what are those called? Block. Nice, block. Okay. Let's move to subsetting. So we'll learn about a lot. This is actually a good section. So we'll learn a lot about subsetting in the next chapter. So I'm not going to dive into subsetting here, but let's talk about some of the particulars of subsetting that make it disadvantageous to use a data frame. And a reminder that the author is one of the main developers for the Tibble, or was part of the team that built the Tibble, I think. So take that into consideration, but they do have the user's experience in mind. So he nicely says this is his opinion, but there are these two particular subsetting behaviors that come out of when you're accessing information in the data type that's a data frame. So here, when you subset this, you'll get a vector. So it's coercing a data frame into a particular type. So this is a bug a lot of times for when people use this. So you're going to want to include drop false here. Well, you have to include drop false unless you coerce your data type into a different structure. So when you attempt to extract single column here, there's also no column X. The data frame, oh, this is terrible, right? It's going to return something similar to the structure. So here, X, for the data frame, if I had a column named XYZ that had a string of A in it, notice that if I use the $ operator in order to access or subset the data frame, it's going to give me the most similar, or what it perceives, perceive is not the right word here, but what it identifies as the most similar object to what I attempted to subset by, and it's going to give me access to that one. I don't have anything named X, but it gave me XYZ. Now a Tibble is a little more stubborn in that it's not going to give you anything. It's going to throw a null. So that's great. Once again, another really useful behavior. Okay, so here then we just, like before, we have this way to make an assessment about if a particular object given as an argument here logically is that object. So just assessing some of the attributes. See that? And you can coerce objects to a data frame like so, or as so. So you can make something a data frame and make something a Tibble. Very cool. List columns. We just actually talked a lot about list columns when we were exploring that linear regression, that simple linear regression example. So maybe I'll be able to save a little time here, but list columns essentially are having structure or referencing lists inside of the data frame itself, and we talked about this before. Okay, so I actually don't know the difference between what gets outputted here. I'm a little curious. So here, what did Y? Oh, so Y broke. It just gave you a combination or concatenation of each of the values exactly as they were. So you have to add this I, which just tells R to evaluate the arguments inside of I independently of what's going on in the argument in itself. So in this case, we want this list structure to be made. And when we do this, we're going to get out these S3 objects, these lists. df2. Let's call df2 here. Let's just take a look at df2 in the viewer. So this is nice. So what the difference here you'll notice isn't that the object was now somehow a list, because it always was a list. It's that the contents of the list was evaluated independently of the creation of the data frame. So before we got this structure where it was just showing 1, 2, or 1 to x, or 1 to 3, or 1 to 4, right? And in this case now, it evaluated each of those and made it so that each of the elements within Y was the evaluated form of Y. So it's still a list, but now we get this nice we get all the contents of it, which is cool. Once again, which is cool. So we're gonna get this rather than just the 1, 2, 3, 4, 1, 3, right? Okay, list columns are really easy to use with Tibbles because you can just include them right into Tibbles. So the challenges or the things that we just described about using this I function, it's called I, right? Or wrapping it in I, you don't have to do that with Tibbles. Tibbles know to evaluate lists in a particular way, so that's not something that you have to worry about with Tibbles. So more cool things. So as long as the number of rows match the data frame, it's also possible to have matrices and arrays in data frames. Which is really funky to think about, but so long as we can have this square, or the length is appropriate, then you can have a 3x3 matrix inside your data frame. So you can have matrices inside the data frame, which is funky, right? And he highlights that approaches with caution. And I also am just thinking about it cautiously and can't think of many cases where at least my brain is going to be able to really wrap its head around a series of matrices within my data frame. I don't know, like, oh no. Oh no. Okay. Where is data frame? So, data frame matrix. Right? So in the viewer, we're not really seeing the whole picture here. But if I were to press here, see, I can't even print. It has a hard time printing it nicely. But here, then you see inside of Y, I have this matrix. And then inside of Z, I have this matrix. Funky though, funky. Not recommended. And that's what I talked about. Okay. Can you have a data frame with 0 rows, 0 columns? An empty data frame? Yes. Data frame. Oh, not data dash frame, data dot frame. X. It should just evaluate, right? Yep. We can look at the attributes of this. 0, 0. And it's a data frame. What happens if you attempt to set row names and they're not unique? It probably throws an error, or it changes it in some way. So if a data frame, if DS to data frame, what can you say about its transpose and its transpose? We can do some of that just for fun here. So we can look at the data frame here. Let's look at TDF. First print the DF, you see that? We can look at TDF, gives us that. And then what if we do TDF? Look at that. Cool. See, to me that gives me back the same thing, but you'll notice here that I'm not getting back the object. We'll make something different. And I don't know what the class of this is. Oh, reminder, right, it did the coercion to a vector. It's a matrix array. It's weird. So we had this coercion behavior from the data frame. And that was like a use case. And it even almost went unbeknownst to me. I had to retrospectively identify that this was the case of there being this implicit coercion occurring when I evaluated this statement that altered the structure, or in some sense subsetted. I don't know, weird. As matrix when applied to a data frame column with different types. What does as matrix do? As matrix, give me a data frame. Okay, as matrix. It does coercion, and it turns it into the lowest or the highest coercion. Coercible. So in this case, we know that things are going to land on becoming characters, so everything becomes a character. And this could be different, and we can test this by doing like logicals here. True. See, so they all become integers. Oh, we can make them into integers like this. Cool. Let's go to null, because I'm pushing for it today. All right, null. It's special because it's this unique type, different from the others of what we talked about, the other two vectors. And null null can have attributes, and null, if you ran it through a test, is null, and you can coerce things, I believe, to null. You can just set them to null. To represent empty vectors, they're nulls. Nulls get used, or the vector null is a special data structure that gets used a lot as a default argument. So in function development, you might use null to set spacers for what needs to be user-specified arguments. And so you want to put something there without placing some inherent default. It forces the user of the function to describe that argument rather than setting some default and then allowing it to run under the hood with a particular setting. That's the use case, at least for me, that comes to mind. Cool. So null gets used a lot with empty vectors too. Null is different than NA. Null is like a space. NA is missing data, or missing. Different. Okay, and then these are the quiz answers from the beginning of the chapter. So that's it. Next time, we're going to talk about subsetting. So subsetting is a very cool aspect of our programming language that allows you to extract information from data structures in very short lines of code, and are going to be, or are used a lot for a variety of data analytic applications. And this chapter is cool because it's going to talk about a set of these applications at the end. So we're going to see some use cases in data analysis specifically where we could start to incorporate this knowledge of subsets. Great. And we'll learn about these things. So can be combined with assignments, operators, the different types of subsetting. Cool. And how subsetting protocols might vary as a function of the vector that one is attempting to subset. All of that and more to be discussed next time. So thanks for tuning in today. This was a pretty productive session. I think we covered a lot of ground, and I'm happy to be back on the streaming grind. So So I hope you enjoyed today's session, and I'll talk to you next time.